Hello, fellow foodies. How many of you love hot sauce? We're big fans of spicy peppers in my household, and we have a big bottle of lacto-fermented Serrano peppers in the fridge that my kids douse over just about anything I put on the table. But what makes chili peppers so alluring to our palates? Well, it has a lot to do with pain and how our bodies react to pain stimulants like capsaicin, that hot element that comes in chilies. I knew just the person to invite on the show to discuss this topic, Dr. David Julius. David is the Morris Herzstein Chair in Molecular Biology and Medicine and Professor and Chair of Physiology at the University of California, San Francisco. He's dedicated his career to studying how pain receptors are activated, and he was awarded a $3 million breakthrough prize in life sciences last year for discovering molecules, cells, and mechanisms underlying pain sensation. David's lab is interested in understanding how signals are received and transmitted by the nervous system. And they've exploited the properties of natural products to discover a family of thermo and chemo-sensitive ion channels that enable sensory nerve fibers to detect hot or cold temperatures or chemical irritants. With the aid of genetic, electrophysiological, and behavioral methods, they've determined how these ion channels contribute to pain sensation and how channel activity is modulated in response to tumor growth, infection, or other forms of injury that produce inflammation and pain hypersensitivity. So thanks so much for coming on the show, David. It's great to see you.
Yeah, thanks for inviting me to be here.
Yeah.
Looking forward to this.
Yeah, well, I guess the first question I have is, what drew you to capsaicin? Are you a big lover of hot sauce?
I like hot sauce, in moderation. I'm not one of these people who pulls habaneros out of a jar and eats them
Yeah.
neat. But, I like to put pepper flakes on my pizza and stuff like that.
That's
I think
great.
my interest in this really sort of grew out of a more general interest in something that emerged when I was in graduate school, in understanding the nervous system.
Mm-hmm.
And in just having this fascination with how people have exploited natural products to understand physiology.
Mm-hmm.
And I when I was in graduate school, I didn't work on anything related to this. I worked with two great people who used yeast genetics to understand basic cellular function. And when I started thinking about what I wanted to do for my postdoc, this sort of area, neuroscience, the molecular biology of the nervous system was just really a pathway that was emerging. It was sort of the birth of the of molecular neuroscience around that time. And I was sort of looking in from the outside and thought this would be a fascinating thing to study. And what I really got interested in at first was, and maybe this reflects kind of the fact that I was a graduate student in Berkeley, in the 70s.
Right.
I started getting interested in understanding how people use plants like psilocybin and mushrooms and things like this to really alter their mind state. And what do these compounds do to so profoundly change people's emotional and cognitive states? I thought that was fascinating. And then, I was really like you, very much like you, I was fascinated at this sort of intersection between, cell biology, neuroscience, pharmacology, understanding drug actions, and then anthropology.
Yeah.
And I started reading books by some scientists like Saul Snyder, who really had worked on understanding mechanisms of opiate action and other kinds of drugs, morphine, of course, another natural product.
Yeah.
And then, other people who worked more in interacting with shaman community and trying to understand the roots of discovery of these natural products. And that really fascinated me, looking at this intersection of how people have come to understand anthropological setting, in the anthropological setting, identify natural products or the sources of natural products, then take that into the lab as you do and use chemistry to identify the main ingredient, the functional ingredient, and then take that to really understanding mechanism in the body and putting that all together. So I got interested in that and really sort of more broadly in neuropharmacology. And then, over time, this sort of blossomed into thinking about pain sensation.
Yeah. Well, let's back up for a minute and talk about pain. You mentioned like opiates And
Hmm.
we're currently facing a big opiate crisis. Like,
Yeah.
how big is the problem?
The problem is huge. It's huge because, there's a report from the National Academy of Sciences recently that reviewed this. And, it's sort of a confluence of a number of things. One is underserved medical communities, especially in some rural areas where people do a lot of manual labor and injure themselves, and they don't have access to, sustained medical treatment. So the easiest way to deal with theirs and sometimes serious pain issues and work-related pain issues is to, give them things like OxyContin and other opiates, and then
Hmm.
this leads to real addiction problems. So, but this isn't just in rural areas; it's everywhere. I mean, I hear many stories of people who, everybody thinks of, and this one thing that was noted in this report is that, oftentimes, at least from, days gone by, people think of those who are addicted to opiates as being someone hanging out on the street, a heroin addict.
Hmm.
But many of the cases of people having opioid dependence really stem from their use of opiates to treat some serious pain issues. And then, they become addicted through that route. And this has
Yeah.
affected many, many people in this country. And so it really is an epidemic. It's a very serious problem. The solution, I'm sure, is at multiple levels, in terms of control, better ways of administering or prescribing drugs, other alternative treatments through, counseling and other types of treatments. But, from my perspective and from what I hope we can add to this equation,
Hmm.
it's really to identify new targets for analgesic drugs that are of the non-opioid class, things that can be used to handle persistent pain syndromes without having to tap into the opiate pathway. I mean,
Yeah. And the opiate pathway, the downsides of that pathway are basically the addictive nature of those drugs. Is that
yeah, I
what?
mean, from a purely scientific level, morphine is a fantastic analgesic, at least
Yeah.
acutely. And
Yeah.
the opiate pathway is still a very powerful and fascinating pathway in the body that we normally harness to control pain. The problem is that opiate drugs that people take, yes, certainly addiction's a big problem, um, but there's also tolerance. So you need higher and higher doses to achieve the same analgesic
Hmm.
potency, and then this leads to all these other side effects like constipation, like respiratory depression, which is what kills you when you
Hmm.
overdose on opiate drugs. So it's a whole spectrum of things that include both acute and long-term
Yeah.
problems. So, I mean, it's really a fascinating biological problem. Why do we become tolerant? Why do we become addicted? I mean, these are long-term, really fascinating goals to understand. But in the short term, there's just too many uh, side effects and comorbidities associated with opiate drugs to think that we can use them as the sole source of pain control.
Yeah. Well, we experience pain every day, like even through our sensory experiences in the mouth. Like, can you
Yeah.
tell us a bit more about how does pain reception in the mouth impact our interactions with foods? And I'm thinking
Yeah.
of
Well,
chilies and maybe even black pepper. I don't know if those act on the
yeah.
same
Yeah.
sensors or.
Yeah. They do. But before I say that, I just want to say one thing, which is, pain is not a bad thing.
Uh-huh.
It's a good thing. We need this to protect ourselves. And people who have rare genetic disorders or other kinds of syndromes like diabetes and other things that diminish the ability of the pain pathway to work normally are at great risk for injury because the pain pathway is there to protect you and tell you when you have or when you're about to injure yourself, and then to
Mhm.
initiate the appropriate, protective reflexes
Response.
like taking your hand away from a hot stove. And so if
Mm.
you don't have those reflexes, you're in trouble. But the goal is really to manage pain when it becomes, persistent and debilitating, when it's no longer useful as a warning system, but is
Yeah.
instead really sort of, crippling our lifestyle and keeping us from doing what we normally need to do. Anyway,
Oh, that's a great point, though. Yeah, I mean, I imagine if you're in the kitchen and you're chopping vegetables, you could really, if you didn't have pain, you could just slice right through your finger,
yeah,
or
you
like
would.
you said,
Yes,
yeah.
and children, there's these rare genetic disorders where people are born without the ability to sense pain, And you really have to watch those kids very carefully because they will do things like put pencils through their fingers or hands or go in a sandbox and get sand in their eyes and then get corneal abrasion because they don't know that they're eliciting tissue damage, basically.
Yeah.
And so, you can see in those examples how important it is to have a normally functioning pain pathway.
Yeah.
But then, with injury, like back injury or sciatica or migraine, whatever, the term is that the pain system becomes maladaptive, which means that it becomes heightened and maybe gets activated when it shouldn't be. And then we're not happy campers. Yeah. So in terms of the mouth, well, of course, we need pain fibers in our mouth as well, because you need to know when you've taken something into your mouth that's too hot or maybe too cold or sharp. And so it protects your oral cavity and, your nasal passages and all these kind of things. So mucous membranes and visceral organs, what we call enteroception, they're really, very highly innervated. Your eyes cornea is one of the most highly innervated areas of your body. Even your bladder, if you looked at a histological section of a bladder with all that, and you could see all the nerve fibers in it, it just looks like a spider's web.
Oh, really?
We have nerve fibers basically in almost every tissue in our body, but of course the skin, our ectopic surface, and our things that are exposed to the environment are very heavily innervated. And so we need that to protect ourselves. But, some of the things we eat activate those pain fibers. So a lot of people think that some of these spices that we interact with are eliciting a taste response. And I'm sure there are some things in chili peppers that are also activating taste cells. But the main pungent sensation that we get from the main pungent ingredient, which is capsaicin, at least in capsicum peppers, it's a pain response. It's not a taste response. And it's activating these nerve fibers to basically, elicit a sensation that we describe as hot. We also sort of feel other things, but hot and burning, tingling. And the same thing's true of some of these other molecules that we've worked on, these other channels that you've alluded to in your introduction, that amazingly, through a sort of beautiful convergence of evolution, are also targeted by other sorts of pungent agents, plants. So that includes wasabi.
I was just about to ask, is this where the mustards come into play? That mustard family,
so the mustard, allium, and mustard family of plants. Onions, garlic, shallots, Brussels sprouts. They produce a different series of compounds, not capsicum-like, but these so-called thiosulfonates and isothiocyanates that activate another receptor that's related to the one that's activated by capsicum, and that they also induce a certain pungency that we know and love. And then the third one that we've worked on, of course, is something that maybe some people don't consider as pungent, but still Eccles and others years ago classified these as irritants, and that are cooling agents like menthol and eucalyptol.
Oh, yeah.
In high concentrations, they are irritating, although in lower concentrations, we like them for their cooling effects. And those activate another receptor that's, again, related to the wasabi and the capsaicin receptor in terms of its atomic structure. And that we call the menthol or cold receptor, because it's also activated by cold. And you'll find nerve fibers that express all of those receptors in our mouth, in our eyes, in our skin, etc. So I always tell people, chili peppers, I always say, especially when I'm giving a seminar, we think of them as being a taste sensation. But if you've ever chopped a chili pepper and stuck your fingers in your eye, you know that's not taste.
That's a good point. Yeah, it's pain. It's pain. Well, just going back to what you said earlier about the anthropology of plants, it really strikes me as you're listing these chili peppers, black pepper, your mustards, your wasabi, those the alliums. These are, well, they're all like many of my favorite foods, but also global exploration and trade networks were set up to capture and move, black pepper and chili pepper across the globe because people desired them so much. That's it's interesting. Yeah.
Yeah, absolutely. And, chili peppers, are indigenous to South and Central America. I mean, we tend to think about them as being, first discovered. Some people think that anyway, and I probably thought that before I, worked in this area, in places like, South Central Asia and Korea and China, in certain regions of China where, people use very spicy food. But they're really, indigenous to the Americas, and then taken to other parts of the world by people like Christopher Columbus and other explorers who came and harvested these plants. So you're absolutely right. These are spices just like, the great spice roots, and they were prized for their sensorial, effects, and spread all, and some spices, in particular like capsaicin, I think was used, probably in the same way to some degree like salt has been used, not only to improve the palatability of food, but also especially in times when you couldn't refrigerate stuff. And so you had to mask really, rotting food with other kinds of experiences. And so, you could put spicy food on there and ignore the fact that the meat was rotting. And there is some preservative effect of some of these agents because they do have some antibacterial properties. And the other reason is, I used to wonder, why would people eat really spicy hot foods in hot climates? You think, God, it's hot enough. What do you want to?
Yeah.
But when you eat a chili pepper, that elicits these hypothermic effects. So you start to sweat, and then you vasodilate, and it decreases your core body temperature. So eating hot, spicy food in a warm climate is a way of shedding body heat and lowering your core body temperature.
Well, that's fascinating. I had no idea about that.
Yeah,
Wow.
so that's another reason people like chili peppers in places like Mexico or Central Asia, places like that.
Yeah. So what are some of the biggest insights or aha moments you've had from your work? You've got such a large body of work in this space, but I'm like, were there any early discoveries that just really hit you as this is really fascinating?
Well, yeah, there have been a few, I guess, those eureka moments. Certainly cloning the members of these families, cloning these receptors, especially the capsaicin receptor initially, which is work done by Mike Caterina when he was a fellow in my lab. He's now on the faculty at Johns Hopkins. He cloned what at the time we called VR1, now called TRPV1, which is the capsaicin receptor. And, that was a great thing. Well, so why was that so exciting to us? Well, people have been looking for this receptor for many, many years. And I should say that in the history of this little field, the initial work really sort of linking capsaicin to cell biology was done in Hungary by Jansko Gabor and his colleagues. And part of the reason for that is that, paprika is a pretty big industry in Hungary. So working with that and understanding its properties is important. And he and his colleagues showed that capsaicin was an excitatory agent for a subset of sensory neurons, which he hypothesized were what we call the nociceptors. So there's a subset of sensory nerve fibers that are called nociceptors, and those are the cells that are dedicated to pain sensation. Because not all our sensory nerve fibers in the somatosensory system are dedicated to pain. Some are for light touch and proprioception, but there's a subset, maybe depending upon the animal you look at, a third to a half, that are dedicated to pain sensation. And so he floated the idea that capsaicin was a way to identify the subset of cells that were involved in pain sensation. And yet, for many years, it was sort of this little mythical site. Is there really a defined site at which capsaicin acts? And really, even up to the time when we cloned it, there were papers coming out that says, no, there's no specific molecular site. Capsaicin just does some funky things to the membrane of the cell, which never really quite made sense, because otherwise, how do you get selectivity?
Yeah.
So we kept looking, and many, a number of labs had been looking, because this was really like the holy grail of molecular pain research at the time. It was like, wow, how does this work? And the idea was, it was really analogous to work of people like Hughes and Kosterlitz or Snyder in identifying the first opiates and opiate receptors. You knew that if you could figure out how morphine worked, you would open up a window into understanding normal physiological mechanisms that control pain sensation.
Yeah.
And for capsaicin, it was, very much the same kind of feeling, and yet it was this elusive, target. And so when we showed that, in fact, there is a molecule that we could call the capsaicin receptor, and that it had the properties that, had been associated with how capsaicin works, that was a pretty exciting moment, I'd say.
Yeah, for sure.
And then, also by analogy to morphine, it's okay. So now you have a receptor for a natural product, but why do we have this thing in our body? We didn't evolve these molecules so that we can appreciate all these natural products. As much as we love natural products, that's not,
Yeah.
why it's sort of more an accident of convergent evolution. And so, what are these receptors doing in our body? And then, figuring out that this receptor is activated by heat was a very exciting thing, because it sort of put the pharmacology together with the physiology. So those were cool moments. The other one I'd say was identifying the menthol receptor as a cold receptor, because that sort of rounded out the picture and gave us more of a kind of a unified, model for how we sense changes in ambient temperature. So that was kind of cool. No pun intended. And, another thing, I won't go through all of them, but another one that I think was really a lot of fun was work that we've been doing over the last, 7 or 8 years with my friend and colleague at UCSF, Yifan Cheng, who's a, world expert in using this technique of electron cryomicroscopy, or cryo-EM, to look at structures of molecules. And we got together with Yifan, a fellow in my lab named Erhu Kao, who's now professor in University of Utah, and Mao-Fu Liao, who was in Yifan's lab, who's now has his own lab at Harvard. We got together as sort of this little group and decided, well, maybe we could use this technique to see what the structure of some of these channels might look like. Because so these channels, these receptors for wasabi, for capsaicin, for menthol, they belong to this family of ion channels called TRP ion channels, which were initially discovered in Drosophila, in phototransduction system. But their role in mammals is, until that time was really sort of not very well understood. And so identifying natural products that activate these receptors, these channels, was really an exciting thing for that field, outside the pain area, because it finally provided some pharmacological tools to ask how these channels work and what they do in our bodies.
Yeah.
And so these sort of spice-activated channels, if you want to call them that, have now served as initial models for understanding what these channels look like. And it turns out TRP channels there are many different types in our body, many subtypes. They're one of the most highly represented ion channel families in vertebrate genomes in our own bodies, in human, in mammalian physiology. And they're really sort of an important, most drugs that people take hit membrane proteins, including ion channels. So we want to know more about them. And, and we were a little embarrassed in this field because TRP channels were, some of the most plentiful in the body, yet compared to other membrane ion channels, we were always sitting there wondering, when are we ever going to get a structure for one of these things? And we were really behind the 8 ball on that. And it just turns out that these proteins, they're hard to work with. And using methods like X-ray crystallography just didn't do the job. So so we decided to sort of take a different approach. And that turned out to be a really exciting moment for 2 reasons. That because we were able to get the structure of capsaicin receptor with capsaicin bound in its pocket.
In it. Wow.
In its side. And then there's another aspect that I'll talk about in a minute that also relates to natural products. And the exciting thing about that was that, that was really interesting for people in the TRP channel field and in the pain field. But it was really of interest even outside that area, because this was the first time that anyone had used this technique of cryo-EM to get the atomic structure of a membrane protein without crystals, which, at least for the cognoscente, that was a big deal. And for the generalists in the audience, that was a big deal because membrane proteins are very hard to work with and to get atomic structures to see what they look like in 3 dimensions. And this technique now allows people to do that sort of much more easily and at a much faster pace. And so the capsaicin receptor was kind of like the founding example of using that technique on these types of molecules. And so that was kind of a ripple that went outside of our field to a much more general field of protein structural biology. And that was really exciting. And you always wonder, what are we going to learn when we actually see what the thing looks like in 3 dimensions? Because we kind of know what it does, and we know drugs are, but that expression, seeing is believing. When you see the atomic structure, it not only becomes informative over time, but it's just a beautiful thing to see.
Oh,
and it sort of puts things together. And the other thing that told us is, so on another natural product route, plants make things that activate our pain pathway. Presumably, we don't really know, but presumably, in some cases, that happens to protect the plant from predation. Right, so if a squirrel or deer starts eating a chili pepper, you go, I don't like that too much, and moves on to some other more edible thing. Because unlike humans, they haven't developed the ability to do things that hurt themselves. We smoke cigarettes and drink alcohol, and we eat chili peppers, but there's other creatures on the planet, other beings, life forms that have to defend themselves. And so we've tapped into those as natural products, as many neuroscientists have, namely toxins from things like spiders and scorpions and et cetera. Wow. And some years ago, we identified a toxin from a tarantula that also activates the chili pepper receptor. And this is really kind of a fascinating thing, because it really is a beautiful example of convergent evolution, right? You have a spider and a plant that both make natural products that attack the same molecular target, the capsaicin receptor, but they do so through completely different chemistries, right? Capsaicin is a small vanilloid compound. The spider toxin's a much larger peptide, small protein. And we found one that has a very high affinity for the capsaicin receptor, and our initial structures showed not only capsaicin bound in its pocket, but it also showed the chili pepper, the spider toxin, draped across the top of the ion channel where the toxin sits to regulate its activity.
Wow. It's amazing how nature can give us so many important clues to understanding the fundamental processes of pain, and to really advance in the field. I mean, if we don't have this understanding, it's difficult to advance and develop new drugs without understanding how these channels work, right?
Absolutely. I mean, the reason that these channels, so there's like 30 members of this trip channel family, and the ones that really, initially at least, that were, that could be studied most readily were these pain related channels. Why? Because we and others were able to find natural products that we could use as pharmacological probes, as drug probes, to understand what they do in the body, how they work as sort of molecular machines. So having drugs, whether they be man-made or natural products, is really essential to probing these mechanisms and, cracking these puzzles. And natural products are really we can tinker in the lab and make compounds, not we, but, chemists. But nature's had, millions of years of evolution to come up with these fits. And that, a fit between a molecule, between a natural product ligand and its target. And so, why not take advantage of that? It's really, an amazing thing. And the place to look for that is either random screening, you know this better than I do, or through following, human behavior and trying to, zero in on sources of interesting molecules based on folk medicine and, these kind of things. Look, some of those hits are going to be goofy and they're not going to lead anywhere. And there'll be more, mysticism than anything else. But, there's enough examples to know that there are some great hits out there that people really have studied and understood over hundreds or thousands of years. And, if you look in the pain field, the two main types of analgesics that we take today, namely opiates and non-steroidal anti-inflammatories like aspirin and ibuprofen, they have their roots in plants and folk medicine, right? Opium, of course, for treating pain, and then salicylate or willow bark for treating pain, which is really the root of discovery of aspirin and all those so-called NSAIDs like ibuprofen and those kinds of things. So it's at least if you just look at the pain field as an example, the yield from understanding natural product chemistry has been huge.
Oh, absolutely. I'm thinking even like our advances, you mentioned morphine earlier with recovery from surgery, but also, the paralytic agents that we've gotten from nature as well, and numbing agents. If you go to the dentist, you think about the cocaine, compounds, the cane derivatives, and curare poison. That was originally researched and helped to relax muscles during surgery so you could have a cleaner cut. It's fascinating, and I think it's an exciting space to be in. And I'm really looking forward to seeing all the cool things I know are going to come out of your lab in the future as you probe these channels more and more.
Yeah, we're still using structural methods, and students who come to my lab in particular, they're always fascinated by the natural product world, or some, not all, but there's always something new out there to find. So as we keep screening with collaborators like Glenn King in Australia and others, and Elda Sanchez at the Natural Toxin Research Center in Texas. We're always asking them for new venoms that they might have and things like that would be sources to screen through. And then, we do the work of finding the active component in there. But, just when you think you've kind of saturated things and, why should I look for another toxin for this target? We already have some. You'll come up with one that acts through a completely different mechanism that, tells you about a new regulatory site on these channels. That's not only fascinating and probably tells you something about endogenous pain pathways, but is yet another, potentially key locus to modulate with drugs for therapeutics. So, I think together with rational drug design and screening, small molecule screening, in the lab, I think all these things really help to help us better understand these molecules, and will add to the body of knowledge that will help us come up with drugs. Because just getting a blocker for these channels is sometimes not enough. There are antagonists for the TRPV1 channel, for the capsaicin receptor. They have some on-target side effects that have been a little problematic. Like as I told you, when you take capsaicin, you experience hypothermia, so your body temperature drops. That's why people like to eat them in hot climates. But if you take an antagonist, your core body temperature may go up a little bit, so people report feeling feverish.
Interesting.
If you block the receptor, then your ability to discriminate something hot is impaired a bit, and so drug companies worry about people drinking something hot and burning themselves.
Yeah.
So what's the answer to that? Well, maybe it's to find drugs that hit other pockets on the channel, that don't shut it down completely, but that interfere with the ability of inflammatory agents to change the activity of the channel, which is really what we think drives pain hypersensitivity through that receptor. So, there's a lot of sites, there's a lot of ways to skin a cat, as they say, and there's a lot of sites on these channels. And hopefully, maybe I shouldn't use that term these days, but hopefully, I have a cat. There's different ways to tweak these molecules. And as you know better than I, drug design and development is a long-term process that just requires, at some point, a lot of trial and error and trying different compounds that hit different sites, even on the same molecule.
Well, that's great. Well, this has been fascinating insight from the palate to the pharmacy of the role of things that we can sense and how it can give us insight into more global pain modulation. It's great. Thank you so much, David, for coming on the show. It's great to have you. This is Dr. Cassandra Quave, and you've been listening to Foodie Pharmacology, the science podcast for the food curious. We're recording remotely on Skype during COVID-19. If you'd like to listen to this and other shows, check out our website at foodiepharmacology.com. We're also on Apple Podcasts and any other major podcast streaming service. You can also catch video versions of the show at my YouTube channel, Teach Ethnobotany, on YouTube. Thanks so much for listening. Stay healthy out there, and I'll see you next time.